the topic is about broadcasting on trees, and I wanted to do it to make it more attractive. So at the beginning I said broadcasting on trees and cryptocurrency. The cryptocurrencies are down, and there's nothing to do with broadcasting on trees. So I write down that. And I'm going to tell you about some. So when you look at broadcasting on trees, there's sort of two motivations that I think one of them many of you have seen before, and that's the block models. And there's a lot of literature and a lot of connections. But I sort of want to motivate this talk from a different direction, in sort of a more philosophical question related to deep learning. So it's not really, I'm not going to tell you anything about learning why ChatGPT works, but sort of some abstraction, why you might be interested in this topic, right? Which is just a different question. I'm trying to go to the next page. Learning. Okay, so here is what we want. One reason to look at the broadcasting on T. One reason I think it's interesting to look at this question that we was studying before. This is an abstraction I came up with a few years before. Maybe really understanding deep nets is too difficult, maybe too difficult for me. But the question is, can we find some reasonable data models where you understand why you need the depth? It's not something that you can solve with linear models or linear classifiers, for which you can prove that there are algorithms that actually do the inference, or maybe even robust algorithms. And the main thing is that you really want some kind of proof that you need some depth or complexity. And I know that many of you are thinking about statistical computational gaps, and this is different. Because when you're thinking about deep nets, when ChatGPT works, it's solving a hard problem, but it does it very fast. So this is not going to be NP hard problem or something that we believe that runs in exponential time. It's something that runs very fast, but still it's not linear regression. So the level of complexity that we're talking about is different level of complexity. It's a level of complexity that's measured in a different way, not about running time that's exponential, not in terms of NP hardness, but some level of complexity. The most natural is to say you need depth, but we talk about other measures of complexity that try to measure how a simple task, in the sense that it's done very, very efficiently, still uses some complexity. Okay, so I want to clarify this point. This is the distinction from a lot of the computation aspects. Okay, so for me, if you sort of at the high level when you think about models like this, what I'm thinking as the main criteria is maybe realism. You want the data models not to be like completely, I take some cryptographic, construct, I put it in some circuits, I combine 30 times, I apply random permutation, that's my data. That data doesn't look like that. I don't want to do that. And I want there to be efficient algorithm for reconstructions, and I want some proofs that depth of complexity. That's all of this story. Very good. Any questions? Okay. So now this talk has maybe too many slides. So I cannot claim that I'm the only one who thought about this level of abstraction, and I have a bunch of related works. So maybe I just mention one or two, and then I won't mention all of them because a lot of very smart people are thinking about related problems, and I just mentioned some related work, and then we skip because I want to tell you about it. So maybe again to sort of go all the way to the very, very abstract theoretical computer science setting, again, these people didn't think about deep learning. They think about depth separation. I don't know what should I do with this jumping icon. So you can fix it, whatever you want to do. So here's the TCS stand for theoretical computer science. And theoretical computer science people thought a lot about depth, and sort of here is some of the best results. So here's the data. The data is xi, yi is just a bit, and xi is uniform in the discrete cube. And you're looking at very classical theoretical computer science, so looking at circuits and over NOT gates, and the sort of the state of the art of this result is a sort of faster Bosman's billion time, maybe 6 years ago, something like that. So they give an explicit, it's important, what hard about this business is this, an explicit construction. It's not some randomized construction. Randomized constructions are very easy. An explicit construction, an explicit function, which is a depth D circuit, such that any circuit of lower depth, of depth d-1, that has non-trivial correlation with this function, has to be exponential size. So it has to be exponential not in n, but in n to the power 1 over t. Okay, so once you go from depth t minus 1 to depth t, if you want to actually be slightly correlated with the function that you're after, you can do it, but the circuit will have to be very large. The original circuit was of size n, your new circuit is going to be of size n to the power 1. So that's very strong separation, in terms of depth. You really need the depth here. But can you recover this? Is this, if you get data from this model, can you recover it? Is it a realistic model of data? Probably no, right? So, if you're just interested in the depth, these are the strong results that you can sort of hope for. It's explicit. Very good. Maybe I'll do one more, just to give the context before. So this is maybe the most, one of the most elegant and work in this area is in people doing theoretical machine learning. Is work by Matos Stergowski. I don't know if you have the theory here, but Matos came up essentially saying, one of the things that deep nets can do very well is they construct fractals. Because if you have something that has many layers, you compose it over and over again, you can get from this picture to this picture to this picture, and this is something that we know from dynamical systems. Fractals is something that you can get by applying a very simple dynamical system over and over again. And what did Matos prove for this? He gave a construction of a circuit of size order t squared, the depth is t, and again, every function that has to agree with t, now it's a real-valued function, but every function that the expected value of f minus g is small, maybe less than or over 100, has to be of size exponentially. Okay, so the original construction, so there's some construction. Right, so let me just explain the parameters. So it's not as strong as the previous one. Here, the t square is both the size and the depth. And what we are comparing it to is we are comparing to a net of depth d. So we go to the square root of the original depth of the network. If you go to the square root of the original depth of the network and you ask, can you do it? You can do it, but you have to be exponential inside. Right? So it's a different kind of separation. It shows you that, at least in some sense, these fractal pictures that you see, you can generate them with deep nets, and they're hard to generate with shallow nets. I don't think that Matos is very smart. I don't think he thought about, this is really a realistic model of data. But I think actually there's something to think about, how much can we generalize it and to what extent can we recover these networks. But to the best of my knowledge, nobody has done that. Right? So we're good? Okay, so there's a bunch of other models, I'm not going to talk about this, I'm not going to talk about that, I'm not going to talk about that, I'm not going to talk about that, I'm not going to talk about that. And even this doesn't cover a lot. Right? There are a lot of smart people working in the related area, and I'm not going to cover. I'm just going to give you my take on this topic. So I'm going to talk about the broadcasting on tree model. So I learned from Yuri to call it bot. He calls it the bot model, and Yuri is also going to talk about broadcasting on tree model later this week. And this sort of, it's also some kind of a fractal picture, so I'm going to draw the picture for you. The picture is, it's a very simple graphical model, so it's a directed graphical model, and it's going in this direction, it goes down, and what you do is, you start with here with one of Q colors, it doesn't really matter how, you apply Markov chain, and here, you apply the same Markov chain, and here, you apply the same Markov chain, and here, you apply the same Markov chain, and here, and so on, so forth. So, everything can be generalized, but for simplicity, just look at the array tree. So this is the binary tree. And let's make all the n the same. And maybe one of the most interesting cases already, this interesting special case, which is identity plus one rank matrix. And the way we usually parameterize it, so maybe I'll write this exactly. So one of the interesting cases, you look at theta times the identity matrix of size q, plus 1 minus theta times the rank one stochastic matrix, right? So maybe I try a little more explicitly. So it's theta times this probability theta you copy, and this probability 1 minus theta you randomize. Choose a uniformly random state or color. So that's maybe a lot of what we talk about today. And just in terms of notation, so we didn't think about this process going for a long time, but given how I use the board, we're going to call this x0. This is just what we have on the board. We're going to call level L, we're going to call x8. First with some notation. Okay, so let me not talk too much about philosophy. This is not a model of switching images, but this model uses and models like that I use for data. Some, you know, even when we talked about some Bayesian trials, many of them have essentially this kind of form with some hierarchy. I'm so glad I mentioned that. So this is a very simple multi-layer generative process. You know, it's used in biology. It's used, you know, it's a special case of Bayesian model. So for me, this is a reasonable model of data. I mean, it's a matter of taste. There's no point discussing this too much. And now we come to the main sort of point of this talk. So we will be interested in the inference problem. So, you know, the way we think about it is in terms of inference is we have x is 0. From x0, this process generates xh, and our goal is from xa generate back or estimate x0 or maybe x0 tilde, some estimate of x0. Okay, so we go from x0 to xh, and from xh you want to do x0. And this sort of fits what I talked about at the beginning, because so in some sense it's very easy, because you know what do we want to do? You know, the model is completely specified. It's a Bayesian model. Everything is specified. You can compute exactly what's the expected value of x0 given xh, and in fact you can do it in linear time. And you know the way you can do it in linear time, you know, this is, you know, it's the fancy names for this is to call it leaf propagation. The less fancy name is to use Bayes' law and recursion. So this is easy to do. It runs in linear time. But already in what I'm saying, you know, you say Bayes' law and recursion. And you know, recursion already has some flavor of text. So this is why, you know, maybe you're thinking this is a good model for the kind of thing that we're thinking about. It's easy to do, like the kind of thing that our phones do. But you need recursion, so maybe there's a, you know, maybe there's an analog of the story that at the beginning you want an algorithm that works. It runs fast, but it's not simple. It's not like linear regression. Okay, so that's the direction of the talk, and most of how I'm going to motivate most of the results and the conjectures that I'm going to. Good. Okay, so before I do that, I have to, you know, so. This topic is somewhat complex, and I'm just going to verbally make a comment about two kinds of different algorithms. One kind of algorithm is getting x not from xh. The other one is actually from the data. So this is question number one. Let me try to use this spacing. Question number two, in the language of this workshop, is not the graphical language. Right, so if you think about ChatGPT, what Google or what OpenAI did is they used a lot of computation power to come up with the language model, the ChatGPT. So they solved a big algorithmic problem to learn something like a graphical model. Of course, there is not a graphical model, it's something more complicated. But you know, you want to be able to do that, and then when you run it, you want to run very fast something like this. Okay, so there are two different algorithmic tasks. One is to recover the big graphical model, and the other one is from the graphical model actually to inference each time. So now I'm talking about question number two, and I'm just going to tell you that question number two was studied because biologists care about this kind of graphical models, and you know, computational biologists solve these problems. So there's work of Tergo, Steve, Sekeli, and Mordo from the 90s, and you know, follow up by us, and we understand this. We can solve this problem in polynomial time. That's a solvable problem. I'm not going to get into the story. I mean, we know how to solve it. You can do it in polynomial time. It's not super fast, but you know, it's something that you can imagine. Very good. So that's about question number two. I'm not going to talk about it anymore. It's something we can do. It's old news. I mean, there are obviously always more of a question, but you know, that's not the focus of this. Okay, so the main question is really about question number one. We want to understand if this, how hard is this easy? How hard is this evaluating the root given level h? We know that we can do it in linear time. We do it in some recursive way. Can we find some signature of complexity that tells us if it's easy or hard? Before we do that, we have to think a little bit and say maybe, you know, we're a mathematician, we think about a symptotic problem. So a simple question that, you know, is do you need depth or complexity in order to classify is the question. Maybe this question is just doesn't make sense because in the limit it's stupid. And for this you could say, what can I say about the conditional distribution of x naught given xh for random xh in the limit? Maybe it's trivial, maybe it's always trivial and then it's not interesting. The data doesn't tell you anything. And even this question, Jim asked me at the beginning, we don't always know the answer. So it depends on the parameter, we don't always know the answer. I'm going to tell you a little bit about what we know. Some recent progress, including by Young-Tak, who's sitting here, and you know, and some of the physicists with conjecture. But this is just to give you a highlight of it. Let me erase some stuff now that so you want to understand this easy thing, but sort of a preliminary question, I hope that you see, is the limit expected value of x given x not trivial in the limit? So maybe it goes something that is independent of h, of x h, right, in the limit. So that's the question number one. And this question was studied a lot. I'm going to, again, I'm covering some literature. So it turns out that the parameter theta is, you know, quite important in this context. So very generally, if t theta squared, t is the number of children which has not. If t theta squared is bigger than 1, then this limit is non-trivial. What is theta in more generality? Theta is the largest non-trivial eigenvalue, non-one eigenvalue of the matrix F. So, you know, there's a theta for every m. Now, there was work in the 90s, starting by Blecherowitz and Zagrebnov. It says that now something interesting starts to happen of the physics flavor. For those of you who've seen physics, Q starts to play a role. So what was Q? So we are looking at this matrix, which I just erased. We are looking at this matrix. So this is a Q by Q matrix. This probability theta I copy, and otherwise I randomize. And somehow the value of Q, the number of samples that I have, starts to play a role. And if you see statistical physics, this is like the differences between Potts model with different number of spins, right? So it's the same flavor. In fact, it's the same model. So the case that was the easiest is the case that Q is equal to 2. And in this case, if d theta squared is less than 1, you cannot asymptotically this goes to trivial, it's 0. And what we know now, this is also true for Q equals 3 and 4. So when you know the Potts model with 3 and 4 spins, it's the same. And this is not type for Q greater or equal than 5. But for general M's, this is not for the case of different Q's. For general M's, in fact, there are Markov chains where this theta is 0, and this will play a role later in some understanding the picture, in which you can recover the roots better than random. Okay, so if you're confused, that's okay. So theta is the most important parameter here that you would think about. In the case of the symmetric chain that we're talking about here, this is the only parameter in the picture. In general, theta is the second largest in absolute value eigenvalue of the matrix. Okay, so you can define it for every m, and you can check for consistency. You know, just looking at this picture, it's clear that the second eigenvalue is the theta. The eigenvalue 1 and the second eigenvalue is. So the Kesten-Stigum theorem is true for every m. It's also true for random trees and so on and so forth. This question is hard, so maybe we first analyze on a specific case where we just have this simple Potts model. For Potts model, for Q, Kesten-Stigum boundary is tight, for Q equal 2. For Q equals 3 and 4 sort of, if the degree is large. It is not tight when Q is greater or equal than 5. But in general, sometimes even when theta is equal to 0, you can recover the root from the groups. Good? This is the picture. So let me give you one more slide on this, maybe on the list. Just explaining the so recapturing just for the specific case. This is not the general case. The specific case of the Potts model where it's this matrix. So I'm proving that if Q is greater than 5, we can reconstruct because the K is bound. It's not the type bound. If Q is equal to 3 and the degree is large enough, there's no reconstruction. The new result with Young-Tak and Alan talk about the critical case. Again, like other spin system, Q equal 4 is a critical case. So if D is large enough and you're below the Kesten-Stigum bound, there's no reconstruction. If Q is 4 and D is small enough and the model is antiferromagnetic, then you can reconstruct below the KS bound. We also extended it to random trees, which has some implication with the block model, but I don't want to go over the block model. And this proves the results by physicists and friends, in particular some of this paper of this group of physicists, and one the conjectures by Moore and Florent and other people. that's sort of the best picture that we have right now. So what's interesting here is that the case Q equal 4, even the degree plays a role. Right? So something very, very important. So, yeah.
And I think you said above 5, what happens?
So above 5, you can do below the case bound. You don't know exactly when it starts, but you can go below the case bound. Okay, so in many of the results, we don't know the threshold. Actually, a lot of open questions we don't really know. But so this is just a sort of a rough question. Can you do below the case bound or no? Right? So the answer is above Q equal 5 you can. Below Q equal 3, we sort of believe that not. We do it for high degree. Q equal 4 is complicated, what you would call, and so on. So this is just a preliminary question of where can you do better than that. Okay, so hopefully you remember some of it. I'll try to remind you more. And again, the question is, we look at this classifier, we can do it in linear time, do we need depth and complexity? So let me tell you a little bit about what we talk about this. Okay, so let me go over this slide slowly. So now we are in the regime. Want to write somewhere.
So you can go over here.
Say again?
You can use that.
I can use the other side.
Yeah, you fix this one.
Okay, so I want to. So now let me just explain the scenario, right? So we are in the scenario where d theta 1 theta square is less than 1. So this means the Kesten-Stigum bound we are below it. So I'll tell you, we are trying to understand what happens in this regime. But we are in the regime where this is true, but the limit as h goes to infinity of the expected value of x0 given xh, this is a random variable, this is a non-trivial random variable. Right? So this is a non-trivial random variable, so this limit is non-trivial. It's not an atom. Right? It actually depends on this. Right? So we are in this regime, we try to understand what happened in this regime. This is sort of the interesting regime. Why is this the interesting regime? So in one case it's interesting. So one thing that we know that any function f of the counts of xh is asymptotically uncorrelated with x. So I don't know how to write it. Let me write it like this: asymptotically uncorrelated with x knows as h goes to. So what are the counts? The count you're just saying, I'm not going to look at all of xh, it's a very large vector. I'm just going to count how many blues there are, how many greens there are, how many yellows there are, and how many reds there are. I'm going to look at my complicated function of these numbers, and I'm going to try to estimate x. Any function of the counts is uncorrelated with x. Right? So we know that. So should I delegate this to you, Yori? You is going to explain what's robust reconstruction in the structure. A wonderful talk tomorrow.
Maybe.
Maybe. Okay. So another thing that you can do is you can take xh and perturb it. How you can perturb it? For example, you can erase each symbol with probability, erase each symbol with some fixed probability, which is close to 1 but not 1, maybe 0.9999. So you get a noisy version of the x instead of the vector x, just at the last level, the input level, and then instead of looking at, so you get at this perturbed vector, let's call the perturbed vector yh, and then you can ask what's the expected value of x not given yh. So this is something that a lot of people do today when they try to study complexity of algorithms. What happens when you look at noisy data? You apply some noise, you apply that noise, and the answer is that this goes to 0. Or to trivial limits. Okay, so this limit is non-trivial, but you cannot get to this limit just using the counts, and you cannot get to this limit if you start perturbing the data. So there's some signature of complexity. Right? So that's two signature of complexity that we knew before. Okay, the two new signature of complexity, which unfortunately are both conjectures, I'm going to write about them now, and I'm going to explain. So these are all signature of complexity. The new ones is a conjecture that in this case, the conjecture is for the Kohler that if f is a fixed degree polynomial, or for any bounded degree polynomial, f, the correlation between fxh and x naught goes to 0 as h goes to 0. So this means that, again, it's a measure of complexity instead of looking at, so as the conjecture is, it's also written here. Any low degree polynomial, so you fix a bound on the degree of the polynomial. Maybe say I'm looking at polynomials up to degree 100. I'm looking at the polynomials up to degree 100 of xh. Not to explain what it means because xh takes discrete values. But you do some discrete chaos decomposition, or you do the obvious thing. So you look at degree 100 polynomial of xh. You ask, can this be correlated with the x naughts? And the answer is we believe it cannot be correlated. Again, we know how to prove it just in a special case where theta equal to 0. So this is true if theta is equal to 0. And there's a similar conjecture, which I won't state formally because I'm going to talk about it a little bit in more detail. Is something that in terms of circuit complexity, and the relevant class of circuits is what's called NC1, and I'm going to talk about it in detail. Okay? So these are sort of all the results that show a signature of complexity of computing this quantity. That's what's supposed to be like running on depends on our font. So, it doesn't work with noise, it doesn't work if you just summarize the statistics. And these are sort of, new directions of trying to prove the result. It says it cannot be a low degree polynomial, and circuit complexity is partly out. Okay, now I'm going to try to discuss this. Yeah.
I'm a little confused by the first point. The way this is constructed, wouldn't SH be exchangeable, or am I?
It's not exchangeable. It's not completely exchangeable. That's exactly the point, right? So the permutation groups that acting here, the permutation group actually it has a name, it's the semi-direct blah 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 blah. But you can exchange it into subsets. But this doesn't give you Sn.
Oh, that makes sense.
Right? It gives you a smaller group, right? And that's exactly that's exactly again the signature of complexity, right? Any function that's Sn invariant is not gonna work.
Right.
Yep.
Okay.
Yep. Other questions? Okay, so let me try to tell you a little bit more about these two results. So here's the actual statement of the theorem that we proved this for today. So, the condition of the theorem sounds strange, but, in fact, there are many chains like that, so let me explain about the condition. For every Markov chain M, where all of the rows of M are different, and theta of M is equal to 0, so we fix the Markov chain M. It has to be pretty special. All the rows of M are different, that's not so special. But theta of M is equal to 0. This means that if you look at the Jordan form of M, there's just 1, and everything else is 0. There's a log of 0. There exists a constant C greater than 0, and a constant D that's finite. So if you look at the broadcast process with D and M, the process that we have here, then two things happen simultaneously. First of all, there is a function f, such that the probability that if you look at f of xh is going to give you the right value of x0 is at least 0.99. So it's actually telling you the root pretty well. Okay? And every polynomial f of degree at most 2 to the c to the height of the tree has 0 covariance with any function of x0. Okay, so two things. The positive thing is you can actually recover the root with very high probability. This 0.99 we can make any constant, right? You just change the c and d. And the second thing is that if you look at any polynomial of degree at most 2 to the c to the h, which is pretty large degree, right? The largest degree that you can get here is d to the h, has covariance 0 with any function. So for me, this is the signature of complexity, right? You really need a very high degree polynomial in order to do something better than that, and you can do something better than that. And in fact, you know how to do it because the leaf propagation is such function. It's this recursion, you don't think about it as a polynomial, but of course you can write it as a polynomial. This polynomial is going to have a very high degree and it's going to work. Yes?
So a couple of questions.
Yeah.
So first, probably is there some reformulation of the degree statement in terms of the Fourier extension of this function? Probably in terms of the high degree.
So I prefer not to use the word Fourier expansion because it's not a product region. Right? So actually
not a natural thing. Okay.
Yeah, so I mean, working as a Fourier expansion is sometimes I think it's useful for you, but often it's not, right? So I would not think about it in terms of Fourier expansion. But there is way to think about it is in terms of, so what does this actually mean? Let's try to explain this. So this is a good question, because it's hard to understand what's polynomial. So in terms of the vector, I'll just try to explain what this chaos decomposition means, right? So, there is a very easy abstract way to do it. It's not really Fourier. So the degree K functions, you can really think about them as the linear span of all functions of K values. So this is also what we have in the product space, in the Fourier space. So that's really the way to think about it. A degree K polynomial, it just means that you look at a function of K variables, another function of K variables, another function of K variables, you sum all of these functions up, and you're going to be your degree K function. Okay, so that's all. So this we do take from the Fourier theory, but that's the right level of abstraction. We don't think of it in terms of autonomous basis.
And another question, which is about point 2 and 3 that you erased, but it's fine. At least I remember that. So it seems like there's this. You also mentioned chaos. Is it related to the chaos that we understand in this like spin glass models, where if you perturb the data, then the set of near optimal solution changes drastically, and so on, which is sort of a kind of a point 2, where you say if you to sort of robust version, you perturb the signal somewhat, then you get something.
Right, so the bigger experts in the room here than me for this question. I'm staring at one specifically. But translating, so this is more about translating question from the tree to random graphs.
Yes.
In the tree itself, we have less of that, right? But how does this things that change in the tree in the replica computations or in this dynamics things that they can see? How did they say? So there are some predictions in physics. I'm not sure. I know exactly what the state of the art of this is now. But I think it's really interesting. Okay. Yeah.
So this covariance is exactly 0? Or?
Exactly 0, and that's why we can prove it. If it was slightly 0, we would be, so we can prove it because it's exactly 0. And I'll tell you what. This proof is actually very simple. I'm sort of going to tell you what the proof is. Because it's 0, it cannot, there are no bounds, right? Something is 0, it's not you're using Cauchy-Schwarz, right? 0 is okay. So let me tell you how the proof goes. The proof is very simple. So let me first of all tell you some linear algebra fact. So like I said, that time is equal to 0 means that in the Jordan form, either the one eigenvalue, everything is just a block of 0, and we know that this means that if you at the power m to the q, the rank of m to the q is 1. What does it mean that the matrix is of rank 1 when you think about it as a Markov chain? It means that when you want q steps of this chain, you forget where you started. So you get something that's completely independent before you started. Right? So this is what and then there's some combinatorial argument. I'm not going to really write it down too carefully, but sort of you can imagine that if the only way, so suppose my q is 2. So this is my q. Suppose the only path to the leaf goes to this path, and there's nothing else. So here I have a path of length q, and this guy are independent. So even if I have a lot of nodes here, a lot of variables here, it's not going to help me because this one and this one are independent. Now, of course, you have to repeat this argument recursively, and you do the counting, and you do it, and you get that you have to have a function of so many variables in order not to independent. And then we have this definition of what does it mean to observe the degree K function. So degree to CH polynomial is just linear combination of such function, and that's the end of it. Right? So it's very combinatorial, very direct. We don't know how to extend it to theta is equal to 1 over gazillion. We don't know, right? When we change things a little bit, not yet, So if we are maybe a little energetic, we can do it in a little bit, but we don't know how to do it. We're good? Okay, so let me talk a little bit about the circuit complexity results, which are actually all there. Just so you get some exercise before the lunch break. Who has ever seen the class NC1? So, that was my expectation. And so, the issue again is like we've all seen P versus NP, right? We've all seen P, but here we want to classify something as hard, even though we can do it in linear time, right? So we really have to go to final complexity classes, right? We really have to talk about it. Final complexity classes. In the right complexity class here is the following: NC1. NC1 is the class of all the log n circles, in which you use just n and o's, not not majority gates. Whatever. There's something that's called TC0. There's the P versus NP in this very, very small world of small circuits, because the TC0 versus the NC1 question. Maybe it's the beliefs that are not as strong, and it's already the same. But the two questions that we had this Anko Moitra and Colin Sandon is that in terms of what you need to run belief propagation, in terms of what you need in order to compute this with arbitrary accuracy, so you can compute it with arbitrary accuracy just using the class MC1. You don't need a bigger class in order to compute this. You can just essentially write, because remember, what is n here? N is the size, the number of leaves. Right? So the number of layers in this recursion is log n. If you want to implement a log n level recursion, you could use this log n level circuit. It's not completely trivial because this is binary and we were talking about real numbers, so you have to care about approximation, but you can do it, right? So one can classify as well as BP in NC1, and there is one broadcast process, only one broadcast process for which classifying better than random is NC1 complete. There is one specific point, we have a bunch of Markov chain. I think the smallest Markov chain that we have is like 60 states. So we have one Markov chain of 60 states, but if you can classify better than random, classifying better than random for this Markov chain is NC1 complete, so you really need these steps in this notion of depth complexity. But as I say, in circuit complexity, we don't even know that you cannot do these log n circuits with majority gates. This steps 5 or something else, so there's this issue coming for complexity theory, which there are kind of there's some hint about this. This is more like computational complexity.
Oh yeah. You had a conjecture.
So we had the conjecture
was NC1 complete.
Right. So the conjecture said this is for one specific chain, and the conjecture is that whenever you're below the Kesten-Stigum bound, it's NC1 complete. Okay, so the conjecture is it's much more general. Again, we use something very combinatorial. I thought I had this slide with the and I'll do this intuition for the NC1 hardness. So NC1 hardness is proved for the one classical problem that is the word problem over the alternating group of size 5. You have the alternating group of size 5. You are solving the word problem is just knowing if the product of a number of elements is the identity or not. This is not to be NC1 complete. We are looking at average case complexity, so we have to show that some average case problem of this problem is also NC1 complete. But really the hard thing about this construction is somehow we show that solving this problem is solving an average case of this small problem over A5. And the reason I said that we have 60 states, actually we have whatever. Let me cheat and say we have 60 states. Is the size of A5 is A5 is about 5 factorial over 2, so it's 60, right? So we have 60 states. That's the reason we have 60 states. In fact, we don't have 60 states, we have 60 square states for technical reasons, which I cannot really get into. But it's coming really from this argument. Very good? Okay, so maybe I have like infinitely many more slides. But yeah, so questions are good, and then I want to tell you maybe about one more variant of this one, which I think might be interesting.
Yeah, so quick high-level question. You said earlier, you seem to make a big deal that the earlier construction of Dolgarsky and the circuit depths were explicit. So is it some notion of explicitness here that you care about, or?
No, so everything I'm doing is explicit because they describe the process completely.
Right.
I'm only talking about explicit stuff. Everything I'm doing is, so maybe I should have said it, but everything that I'm doing is completely explicit because I'm describing, my generating process is given by this very simple tree process. It's as explicit as it can be.
Right. So in the previous two models, its explicitness was important because non-explicitly by random construction get trivial. Those results are trivial, but explicitly it's a
for depth separation.
For the depth separation.
For depth separation or for depth.
Right. For you, it's also there's some kind of an implicit, easy way to get the same thing.
No, because everything I'm doing is explicit. My models are all simple, right? There's nothing. They can never be complicated. Right? So I should have said it, but all of my models are explicit by construct, right? I cannot do anything. Good question. Okay, so for those of you who still have some, and I know I dumped a lot of material on you, so to digest over lunch, but for those of you who have some mental capacity, I mean, I just think actually maybe so I have a lot of stuff there, but I just do this one slide, especially since Jimbo is here. I prepared this slide without knowing that Jimbo will be here. So I'd say that that everything that we talked about that was in this slide, I sort of tried to give you the implicit impression that the only interesting case, so before, what I said before, where was the complexity, or until now, is that the complexity appears if d theta squared is less than 1. Okay? Now I want to tell you that even if d theta squared is bigger than 1, there is some complexity, maybe, but the goal now is not to find, so what is the level of complexity, but the task is going to be different. The task is I want to find the function f that maximizes the probability that f of x of h is equal to x of 0. So let me contrast it with what it was before. Before, I wanted this probability before, but I wanted that this probability is non-trivial. Now I want to do the optimal thing. So the difference between doing the optimal thing and doing non-trivial is non-trivial, right? So one of them is so. And again, the motivation from deep nets is very philosophical, but for deep nets, a lot of what people observe is that already at the beginning you get something, right? If you run linear classifiers and images, you get something, and the nets give you more and more and more. So it's not clear if the complexity. So it's really about doing better than random, or it's really about being able to be very accurate. Okay, so that's the motivation for what we're talking about now. And here, very little is known. So I'll tell you a little bit about what's known, but not much is known. So there's one dish paper with Jimbo and Frederick Kohler and Shesh Jain, which looked at some very interesting aspect of this problem. So I told you that you can do this recursion, and this recursion uses real numbers, and people in this community ask what happens if instead of real number you use bounded memory. And in this paper we proved that you cannot get to the Kesten-Stigum bounded memory algorithm, so that's a signature of complexity, that this recursion itself has to use infinite accuracy real numbers. And maybe even in the same setting, just of everything is in the case of 2x2 matrices, symmetric matrices, I'd like to make sort of two conjectures. The first conjecture is that, in this particular case, you can achieve epsilon optimal accuracy with a polynomial of degree d of epsilon, where d of epsilon agrees, goes as epsilon goes to 0, and I would conjecture that d of epsilon actually has to go to infinity as epsilon goes to 0. Okay? So you are in the situation that even the linear estimator, maybe I should say that even the linear estimator is correlated with the root, but now you want to get optimal accuracy, and the conjecture is that to get optimal accuracy, you have to have a degree of polynomial that goes to infinity. It cannot be a bounded degree polynomial. And while we didn't write it in our paper with Anko and Colin, we didn't write it because we had to wait for Guri Polyansky to prove the result. Now, the analog of this for circuits, which is now for TC0 circuits, which I actually didn't talk about, is proven, right? So, we know that in TC0, as you increase the number of levels in TC0 circuits, you can get better and better accuracy, and you actually need number of levels that grows. I believe that. Right? So maybe the second part we don't know. So maybe let me say just conjecture one. Conjecture two, maybe.
What do you mean here? Like proven for TC0?
Okay, so yeah, you can ask this. So what is TC0? So maybe let me start from TC0. TC0. It's bounded net circuits, which is and or not like before, but it also has majority. Okay, so majority gates are very strong because they can count, right? They can count stuff, right? That's very strong. And now you can ask if you have AND or not in majority gates. In this case where you are above the Kesten-Stigum bound, can you get optimal accuracy, not just a little bit of accuracy? If you just do one majority, you get non-trivial accuracy. Can you get optimal accuracy? So what we proved is that if you want to get accuracy 0.01, you can do it in depths that is a function of 0.01. This is 0. In the conjecture 2, which when I prepared the talk I thought we know how to prove, now I'm not sure I know how to prove. Conjecture 2 will say that actually in TC0, as the accuracy goes to 0, the number of layers that you need will have to increase, right? TC0 is actually a very tricky class, so that we don't say that we proved it, because I don't think we proved it, but I think that would be a very interesting conjecture. Okay, so I have a zillion more slides, but maybe I'll stop here, and I'm happy to take more questions. Thank you very much.